Good afternoon, everybody. We'll get started here in just a couple of minutes as folks join in here. We'll go ahead and get started here. The entry is slowing down a little bit, so um, we'll just get started a little early today. Well, 1 minute late, early for me, late for everybody else. So thank you everyone for coming and attending this webinar. Let's just go ahead and get started. My name is Alex Shattuck. I'm Director of Grid Transformation at ESIG. I'm filling in today for Julia. So if you were expecting Julia, I apologize that you're stuck with me today. We've got a discount at your next registration for having to suffer through me today. That's a joke. But thank you. If you see Julia in the chat, please tell her to get some rest. She's sick. She shouldn't be here. So feel free to send her a message if you see her in the attendance to go to bed. So welcome to this webinar. If you're not familiar with ESIG, this is your first time having a webinar. This is from ESIG's side, so the Energy System Integration Group. We're a membership-based nonprofit organization that provides our members with objective information, resources, and networking opportunities that support all things energy systems integration. So we do this through workshops, tutorials, webinars, just like this one, blog posts, working group, and task force activities, which we're going to highlight a lot of in this webinar today, or some examples of some of the working group and task force work, and in producing technical resource materials. So for those of you all who are members, thank you so much for your support. The membership, amongst others, makes these webinars possible, and the other work that we do possible as well. So workshops, monthly webinars, they're open to everybody. So please feel free to visit our website. That's esig.energy, or find us on LinkedIn, YouTube, Facebook, or X or Twitter. So a couple logistics before we get into introducing our fantastic speakers today. Everyone's muted on the line today. Chat's disabled, I believe, as well, just to reduce some distractions. So for those of you who do have questions, you can use our Slido platform, or the Slido platform, with the password ESIG11. And there you can put your comments and questions in. And the way that'll work is when we get to Q&A time at the end, I'll take those questions that get kind of submitted and voted on. So you'll see in the Slido that you can click a thumbs up next to any of the questions that you may think are worth us answering. And that's where we'll start for the Q&A. So you can both ask questions and vote for other questions if you want to see those answered and you like those questions. Any questions we don't get to throughout today, we'll be putting together a sheet and sending out answers to those questions as we have time, along with the material. So even if you see a bunch of questions in there, feel free to ask your question. It will get answered at some point. So don't leave your question out if you think we're not going to get to it, because we'll get to it at some time, even if it's not today. So we're going to try to spend 15, 20, maybe a little longer on Q&A at the end, depending on how our timing goes for these presentations, and we'll wrap it up towards the end after that Q&A session. Once we finish today, we're going to provide an email link, and that will be this video file that we're recording today, also short responses to the questions like I mentioned before, and slides for today's webinar. So with that, let's introduce our topic and our speaker. So the topic of today's webinar is integrating large loads. Very good topic here, and we're going to focus on interconnection requirements, performance requirements, and modeling. So our speakers, just to kind of preamble into the webinar, as large power electronics dominated loads, such as data centers, advanced manufacturing facilities, and electrolyzers are connecting at unprecedented scales, speeds, and penetration levels. we're kind of all facing a new challenge here in trying to mitigate reliability risk associated with these interconnections. The webinar today was going to present findings and recommendations from 3 of the ESIG large load task force project teams. These 3 project teams focused on large load interconnection process and study practices, technical performance requirements and large loads, modeling approaches needed to accurately assess system impacts across planning and operations time horizons. So we'll get a good spectrum of all things that go into interconnection of these, including process requirements and how to actually model them and what challenges come with that. So throughout this webinar, we're going to summarize key gaps in the current practices, highlight some of the best practices that we've seen or members have seen from utilities, ISOs, RTOs, and developers, and also discuss practical recommendations to improve kind of all of this stakeholder process, or not stakeholder process, but improve all of this for us stakeholders in this process. So our first speaker, these are going to be out of order. I'm just going to list them. I guess my first speaker is me. I'll introduce us with a couple slides after this introduction, but I don't count here. So next will be Kyle Thomas, or Parag will be next. So Parag is a technical leader with EPRI. He presents with us fairly often. So you probably heard his intro before. So just keep it short for him. He leads research areas of power system modeling, model validation, and probabilistic long-term transmission planning, and also integrated system strategic planning. Next, we have Ahmed, and he's the Vice President of Transmission Planning and Operations at EPE, Electric Power Engineers, and he's leading transmission analysis, consulting, automation, product development, and advisory services, supporting ISOs and RTOs, vertically integrated utilities, investor-owned utilities, municipalities, and co-ops. And then lastly, we'll have Kyle Thomas, and he's Vice President of Engineering and Compliance Services at Elevate Consulting, and he leads just a very broad number of engineering and compliance activities. And his focus is on building cross-sector collaboration with related to IBR integration and larger integration efforts. So between the 3 of these folks, we have a very strong set of presenters here today. These 3 guys they were the leads of these specific project teams and did a lot of very good, very detailed, very hard work wrangling all of the technical experts and putting these reports and information together. And they'll talk about what that ended up with as we get there. So with that, I'll just get us kicked off here just with a short couple slides. I'll spend just a couple minutes on here about integrating large loads to kind of set the topic here. So Brooke, next slide, please. So if you're here and you're interested in large loads, you've heard of what's happening, right? The load growth we're actually seeing load growth, which we haven't in previous years. The load growth has been relatively flat, just in general. And now we're seeing a big change. And now that load growth is growing again, and primarily this is, can be attributed to large loads like data centers, crypto miners, and things like that. So we are seeing a problem. The data interconnections and forecasts back up this need for coming up with best practices and solutions. So it's important that we talk about it now and get ahead of this technical problem before it becomes a reliability problem. So next slide, please. So this is a lot of work, a lot of content here. It's going to get repeated, I think, throughout the presentation. So I'll go through this quickly. But the first couple questions you might hear is, we have large loads on the system already. What's so different about modern large loads? But there's quite a few major differences. One of them, or first of all, being size and concentration. We're seeing individual loads of hundreds of megawatts to just about a gigawatt, and clustered in very constrained regions and very small footprints. So in the past, where you may have a few hundred megawatt, steel manufacturing facility in one area with regional, driven by regional economics. Now we're seeing the equivalent of 10 steel mills or something in a very dense, very small geographic area, which really kind of lets us think, or leads us to think about how we can handle this massive concentration and of the penetration of these large loads. Demand profiles and flexibility. We're seeing highly dynamic swings, very different load profiles between different technologies. There is opportunity for lots of flexibility, new flexibility, but again, that comes with discussions and collaboration on how to unlock that flexibility. And we'll hear about maybe how to do that and what that means from our presenters today. Rapid and uncertain load growth. There's not a lot of good data out there for how much of the large load interconnection queue is actually getting implemented or integrated into the system, which leads us to pretty uncertain growth forecasts. Those are also very rapid, very steep forecasts. So both of those things coupled together, you get situations where you might have forecasts differing by very large amounts, even from very good forecasting entities. So that rapid and uncertain growth is a very new problem here for loads and power electronic interfaces. The power electronic interface isn't new, right? Inverter-based resources interface with power electronics, but big loads interconnecting with power electronics have the opportunity to add some stability risks for different reasons, like protecting sensitive AI and crypto mining equipment, training cycles, and things like that. So we do need new standards, models, screening tools, and performance requirements that we'll all talk about today. So next slide, please. So at ESIG, we have our large load task force. This was a huge undertaking of content and topics. So to capture this, we broke it down into project teams. So the 3 project teams we're going to hear from today are the interconnection process project team, which is for large load interconnection processes and studies, the interconnection performance project team, who worked on requirements and performance specifications for large loads, and then the modeling requirements project team, which covered modeling requirements for large loads for power systems studies. There are others that there have been and there will be webinars on, like the load forecasting, transmission planning, resource adequacy, and market and operations project teams, who they did very similar work, lots of very good detailed work in their own subject matter expertise areas. So be on the lookout for previous webinars or future webinars, and for these reports as they come out in the near future from ESIG's Large Load Task Force. Thank you. Why do these matter? They kind of map to the risks we just mentioned. Is the large loads are scaling faster than our frameworks were designed to handle. So we have to figure out best practices and methods to kind of fill those gaps and make their interconnection frameworks have opportunities to integrate these large loads and reliable processes. Recent disturbance events are showing that the large loads don't always behave as expected. This is very similar to how large inverter-based resources aren't behaving as expected, which means that we have a lot to learn as far as how to actually model, how to validate the models of these large loads, how to make sure that they're performing the way performance requirements say so, and how the interconnection processes will enable all of those things through process enhancements or potential process enhancements. The previously used load models aren't any longer sufficient. So the kind of old converter-based loads, the converter-based loads need new detailed modeling during interconnection studies. The old methods of aggregating and modeling load may not be sufficient for these large loads, and kind of specialized modeling is needed. And then lastly, just similar to the others, is the actual interconnections aren't keeping pace with the scale and impact of these large loads. So even simpler things like read-through, post-recovery behaviors, and oscillatory interactions, there are in some areas some requirements for those, but we need to expand them similar to what we've done with IBRs, and maybe even more, or maybe even push both IBRs and large load interconnection requirements forward in tandem here to capture this impact. So that kind of boils down to just the fact that we need clear requirements, validated dynamic models, and alignment between studied and as-built behavior. All of those things are essential for reliability. So I think with that, we will hand it over to Parag, unless Julia had one more slide. Perfect. Yeah. So Parag, please go ahead. Kick us off.
Thanks, Alex. Let's bring my slides up. Yep. Good afternoon, everybody. Again, thanks for joining the call today. What I'm going to do is, following on what Alex kind of shared, talk about some of the work that we have completed as a part of the modeling work stream. So as you all know, a lot of you have been part of the modeling work stream calls and the modeling work stream effort where we penned this report talking about modeling. There is a lot of important material that went into all of this. Today's call, I don't want to go through all of that material. It's pretty expansive. I know that it's going to take more than maybe 2 hours to go through all of it. But what I wanted to provide this broader group is a highlight of the key components that exist within that report. And then, of course, I'd encourage all of you to go and read the report as you get your hands on it and sort of see what's in there. So with that, let's move to the next slide here, Brooke. Thank you. So what is the scope of this modeling guideline? Well, we can break it down into 5 key things here. Number 1 is to provide a clear guidance on how to accurately model large load facilities. Now, load modeling has been, it's not a non-existent practice. We have done this in the past. However, there was a lot of approximation that went in. There were legitimate reasons why that used to happen. There isn't really a clear requirement right now, like for generators, to do very specific modeling of plants or any kind of model validation or model submission requirements. And one of the ways to kind of tackle that whole issue was to develop models that were much more approximate. But with experience, we had realized that that used to do a good job at representing the behavior of the facilities. Now, as these facilities have started growing larger and larger in size, there's, of course, the need to look at this modeling from a more lens of accuracy rather than using an approximate approach. So really what this guideline tries to do is provide some insights into how you could develop these models that are more accurate. Now, when you're trying to model these facilities, of course, the next question that we want to ask ourselves, or where we need a little bit more guidance, is on defining what are the different components and what are the different behaviors that needs to be modeled. If you go to any large load facility, they'll have tens and hundreds of motors and small, large components that are running. How do you go about modeling all of these things? If you want to model everything or every single bit in detail, the model of a single facility can be as large as that of an interconnection. So providing guidance on that. The third piece where we try to provide some clarity is on when to use different type of simulation frameworks. Of course, we know we have positive sequence frameworks, we have EMT frameworks, both have their own uses, both have their own purposes and their own limitations. So we want to clarify which platforms to use. And I'll talk a little bit about that. The fourth piece that we cover in this particular guideline is to provide guidance on how to validate models and verify the parameters if these models are being submitted to you or if you're responsible for developing these models. And then having some sort of a model quality testing protocol that allows a transmission planner or a utility or an interconnection authority to kind of make sure that the models that are being provided to them, they're actually good enough to run the study at hand, whether it be an interconnection study or whether it be an interconnection-wide stability kind of assessment. And then last but not the least, we want to provide some guidance on the gaps that we see today in terms of the practices, in terms of the improvements to the processes that are needed so that we can facilitate all of this modeling exercise, and then recommendations on how we can go ahead and improve the state of the art. So let's move to the next slide here. We had a very healthy group of contributors who actively contributed to the writing of this particular report. I won't go through all the names over here, but I've highlighted the 3 names over there: Poria Astero, Mehdi, and Ali Yazdan Pana from ERCOT. They have been my subsection leads, and they have essentially gotten smaller groups together and contributed heavily as a group to some of these chapters. They made sure that they helped me with coordinating all of that reports. I'd like to just highlight all the effort that they put in getting this particular report out. And I'd also like to thank all of our contributors. I've kind of listed all of the names over here. All the contributors have done a massive job at providing useful material as well as providing feedback when we were going through the review process. So moving on. Yeah, the report has been broken down into the following few chapters. We have an introduction section. We talk about dynamic models for new large loads. We talk about essential components of new large loads. We talk about the modeling requirements for power system dynamic assessments. We provide some guidelines for dynamic model development. We spend a good bit of pages talking about model parameter verification, validation, as well as model quality testing guidelines. We do have 2 case studies where we sort of demonstrate what are the reliability impacts of inadequate or improper modeling of loads. And then, of course, we have a last section which talks about recommendations for accurate large load model development. Like I said, all of the material has been broken down into those chapters. Won't go through all of them, but what I want to do is highlight some of the key things that we cover here. So the first question is modeling for what? Modeling is a very wide or a very overarching term. You could be modeling for a lot of things, but this particular document specifically talks about modeling for positive sequence, phasor domain simulators, and electromagnetic transient simulators. So we're talking about the PSSEs, the PSLFs of the world when we talk about the positive sequence phasor domain tools, not just the 2, but all the ones that fall in that same category. And then for EMT, these are the PSCADs, the EMTBs, and all of the tools that fall in that particular category. So this is kind of the modeling that we are talking about in this particular guidance document. Now, if you're doing that kind of modeling, what are the issues that you're typically trying to address? Well, these issues are your rotor angle stability issues, your voltage stability issues, frequency stability issues, resonance stability issues, and converter-driven stability issues. So all these simulators that I'm going to talk about and the modeling associated, or the associated modeling for these simulators, they kind of cover these range of problems. And this is kind of described in the introduction section of the document. So if you're going through the document, you'll realize that what are the classes of modeling that this particular document is covering. Now, as we describe or as we go through the guidance that we want to provide for modeling, this particular document also provides a brief introduction to the load modeling practices in US and Europe in terms of what is being done here today, what has been done in Europe as we know about it now, and it also provides a brief summary of the WEC composite load model. So the WEC composite load model, folks who have been using this know that this is the latest state-of-the-art model that we use for modeling residential, commercial, and industrial loads. We do provide a brief summary of this model. We also highlight why this model wasn't sufficient to sort of represent some of these new large load facilities like crypto mining facilities, data centers, hydrogen electrolysis, etc. So we kind of point out what is the biggest drawback of this particular model and why we went down this path of having a modeling guideline and renewed efforts with trying to model large scales. So moving to the next slide here. So the first key idea that we cover in this particular document, and folks who have been part of the modeling community for a long time has heard this conversation, heard this discussion over and over again, but we always have a lot of new folks joining in on these calls, joining in all these discussions and reading these reports. So we do spend quite a bit of time talking about phasor domain and EMT modeling. So it is important to understand the distinction between the two and when both are useful. Today, we use both of these models for our modeling exercises, for our simulation studies or interconnection studies or stability assessments and such. The phasor domain tools, these typically cover things which are generally in the less than 10 hertz range. And the idea of these tools is that because you reduce the modeling detail, you can model larger portions of your interconnection. And what you want to use this type of a simulator is to study those impacts that actually affect the bulk power system. So, things like inter-array oscillations, things like transient stability, things like voltage stability, which affect a larger swathe of your power system. That is where these tools are more useful. Then you also have the EMT tools, and we have been talking more and more about these tools as we get into the space of inverter-dominated or converter-dominated devices, where there is quite a bit of fast dynamics that can have a lot of impact. Typically, fast dynamic impacts are much more local to the system. So a lot of these tools are now used for doing a lot of the specialized studies, which generally affect the local power system. So you do some sort of equivalencing of the larger or the broader power system, and you make sure that you model the local system, the system that is local to the load or any other installation that you're assessing. And you do that in a lot of details. You model everything in three-phase details. You model the high frequency control loops and such. And then you use these tools to do those kind of studies. So these are generally the very fast transients that happen. We are looking at the inner control loops of converter-driven devices, which have very high bandwidth. We're talking about instabilities related to phase lock loops, again, which happen at very high frequencies. And then certain interactions like subsynchronous resonances, subsynchronous controller interactions, which might happen at frequency ranges that are higher than 10 hertz. So that is where we use EMT tools. Now, both these tools have their uses. Like I said, if you're looking at bulk system impact, where you want to model the entire system and you want to find the effect of a large load facility or effect of any installation on the broader power system, you generally look at phasor domain modeling. You make some assumptions on the models where you assume that the higher frequency dynamics is kind of damped or they're much more stable, and you try to focus on those slower dynamics which kind of affect the broader power system. And then, of course, we move into EMT studies where essentially the goal is to identify some of these faster dynamics and identify what type of impact it has on the local system, and then identify very specific mitigation methods that take care of all of these things. So again, the guidance has a lot of details around when some of these simulation platforms are preferred, and then if you're using one of these simulation platforms, what are the modeling needs? What are the things that you need to be aware of? So moving on to the next slide here. We talk a little bit more about some of the other modeling lingos that go a little bit beyond EMT and phasor domain. So if you kind of break it down, even between the EMT and phasor domain, you start seeing two different categories of models. One is what we call the generic models, and the other one is what we call the original equipment manufacturer provided models. Now, again, this is a distinction that needs to be understood in the context of modeling, and this again has been discussed quite a bit between folks who are intimately involved in these discussions around modeling. So both EMT and phasor domain, you can have OEM-specific models or generic models. Now, for phasor domain, the generic models, we all know that these are available as library models in most of our simulators. These are white box models. The goal of these models is to provide you something which is a generic representation of an equipment, whether it be load or any kind of power system equipment, with the goal that if you are a planning engineer and you're sitting here today trying to see what the impact of those future devices can be on your system, you should be able to use a model and gain some understanding of what happens to the system, especially in that stage when you do not have the OEMs fixed. We have similar models in EMT as well, the EMT generic models, but the EMT generic models right now, they are generally used more on the research purpose, more on exploratory or risk screening study approaches, because these are very generic. They're not representative of an actual device, oftentimes trying to pinpoint a particular problem and then trying to resolve or find a solution for that particular problem is generally challenging when we're talking about generic EMT models. Now, within both phasor and EMT models, you will find OEM models. OEM models are generally a more truer representation of the device at hand. These are generally black box because OEMs want to protect their IP, so they're generally black box, difficult to understand a little bit, and you might need help from the OEM to actually tune these models. But these are very well suited for resolving some of the site-specific issues, provided that these models have been developed to a certain quality that they can identify those issues and they can help you with the resolution of those issues. Now, that said, with all the modeling, whether it be EMT and phasor domain, one has to always remember that models can always be wrong. It doesn't matter whether it's a positive sequence model or an EMT model. If the model hasn't been developed properly, the model can always be wrong. There are even instances where OEM models have discrepancies and they're not a replication or a good representation of the actual devices. So we have to be very careful when we look at the models. Using a more detailed platform does not necessarily mean that you're doing a better job at modeling. To do a better job at modeling, you have to essentially make sure that the models are a true representation of the device at hand. And these have been meticulously developed to make sure that there are no discrepancies when these are being implemented. So let's move to the next slide here. So what are the key characteristics that some of these load models should represent or have so that they are good for some of the studies? And we won't get into a lot of great details over here, but I've highlighted some of these key items that one needs to make sure that the load models actually represent. So they should have a representation of the active power and frequency control if that exists, if the device participates in frequency control. They should have a good representation of the reactive power and voltage control. So if a large load facility has some sort of a voltage control device, we need to make sure that is represented. It should have a good representation of the load profile. So if the load profile is flat, we should be able to represent that. But with AI training, we know that these load profiles can move up and down. So depending upon what kind of studies we're doing, we need to make sure that these nuances of the loads are represented, because that is going to have a material impact on the study. Right-through behavior is again a key thing that needs to be represented. So if a load facility has a particular drop-off threshold or is able to ride through a certain type of disturbance, we need to make sure that that is replicated properly in the model. If it is not an OEM model, if it's a genetic model, we should make sure that the model has the capability of programming a lot of these right-through behaviors so that we can sort of study the impact of different type of right-through behaviors on the system response. It should be able to model the ramp rate limitations. It should be able to model the mechanical load behavior. So it's not just modeling the power electronic device that is the front end of any kind of load facility, but what happens at the back end also has a material impact on how the device operates. A simple example is if you're running a motor through a variable speed drive, the load dynamics of the motor can also have some impact on what happens to the system. So you should be able to model those things as well. Black start considerations, again, very important. If you're using this model for black starting studies, you need to make sure that you're modeling the pre-charge circuits, you're modeling any kind of controlled startup behavior, or have the ability to model that, or have the ability to represent that in your model, so that if you're reusing this model for your black start study, you're able to model those nuances that these loads have during startup. If you have any kind of on-site generation, you should be able to model those on-site generation behavior. And then very importantly, if you have an EMT model and these models operate on per phase voltages, you should be able to model the unbalanced voltage operation of that particular device. So again, key characteristics or key models, again, I wouldn't say that this is all inclusive, but these are at minimum the set of things that you want to make sure that your model covers and is able to represent. So moving to the next slide here. So what are the key model development principles? Again, these are kind of the important principles that one has to bear in mind as we start developing these models. Of course, very importantly, fidelity to actual response. While developing the models, we should make sure that the models can accurately represent the real plant responses, particularly during disturbances. Again, we probably do not want to try to model the entire spectrum of behavior of the loads. We always have to remember that the models are to be used for specific studies, specific purposes. So we need to make sure that the relevant responses are modeled accurately, and we have the ability to sort of vet that the model has indeed has that level of fidelity. With all modeling, do not let perfection be the enemy of progress. Models don't need to be picture perfect. They need to be able to do the job. They need to be able to allow you to make planning decisions, interconnection decisions, and such. So you have to always look at it through a lens of practicality. So always bear that in mind as you develop these models. Modeling detail, again, having a sense of what is the level of details that is needed for a particular type of assessment is going to be important. If you look at a large load facility, there's going to be hundreds of components within that. Like I said, if you wanted to model down to every single detail, the model of the facility could be as large as that of an interconnection. That doesn't help somebody if the simulations take significantly long time to run. So we need to start thinking about meaningful aggregation. And there are examples of those already. We have done aggregations in EMT for PV and wind farm models. We can go back, look at those examples and leverage some of those things as well. Now, even with modeling in EMT, you have to be very clear about the level of details that you're modeling things to. So for example, if you're modeling the converters, these could be switching models, these could be average models. We know that if you're looking at stability type issues, average models generally do a good job. So we need to make sure that we are able to model those things properly. If you're looking at something like a ferroresonance type of study, you need to make sure that you're modeling the saturation of the transformers properly. So again, these are the modeling details that one has to bear in mind when they're developing these models, because the level of detail that goes into these models are very relevant to the study at hand. Last piece is around numerical stability. When we are developing these models, we need to make sure that the models are numerically stable so that we don't confuse a solver-driven instability issue as a practical system instability issue. So we need to be very careful about the time steps that we're using. We need to be very careful when we are coding these models, how we are coding them, because certain coding styles or certain coding practices can lend to being more numerically unstable than others. So follow good modeling practices. We have some guidances on those in the document as well. But the idea is to make sure that we understand, or we are able to distinguish between a solver-driven problem versus what an actual system problem is. So let's go to the next slide here. Okay, some of the dynamic model development guidelines, again, there is a lot of detail in the report. I'll just go through some of the key things. When we're talking about the positive sequence phasor domain modeling, we need to remember that these are essentially to capture the lower frequency dynamics. So when we are developing these models, we have to always bear in mind what the goal of these models are and how we are going about doing all of these things. Generally, when we develop positive sequence models, the high frequency loops are always considered to be stable. And what we do is we reduce the stable system to algebraic equations, and that's how we are only able to represent the slower frequency dynamics, whereas the high frequency dynamics are all considered to be stable. Now that assumption holds in many cases, but if it doesn't hold, that is when we switch to EMT modeling. We have done this for IBRs in the past, where for weak grid cases, we know that when PLLs are not stable, we want to switch over to EMT modeling to kind of get some sense of what the dynamics looks like over there. But bearing in mind, when we're doing these PAs, these positive sequence phasor domain modeling, it is important to include the outer loop controls, the active power frequency, the reactive power voltage, the write-through logic, etc. We need to make sure that the power flow models are initialized properly. The power flow conditions are the initial conditions for any kind of a phasor domain positive sequence model. So we need to make sure that the power flow is initialized properly. And from the power flow, the model gets initialized properly. So when we're developing these models, we need to make sure that that exercise has been done properly. We need to make sure that the aggregation is done properly because these models won't have a lot of details. There's going to be a lot of aggregation. And when we're doing aggregation, we need to make sure that we provide guidance on how parameters of an actual facility can be tuned or can be changed or modified to fit this more aggregate model. And then, like I spoke in the last slide, numerical stability is important. There are certain coding practices that led to having these models more numerically stable, includes adding time constants when needed. And these are certain things that one has to bear in mind. For EMT modeling, to include all important components within the load facility, including protection and control as needed. Like I said, EMT is more of a blank canvas, so you need to know the kind of studies that you're trying to do and make sure that you've modeled all of those things. The details or the level of modeling detail depends on what type of studies you're trying to do. Again, be careful or be very deliberate about the kind of assessment you're working on and develop the model to that detail, because having a very heavy model doesn't really help. It just takes a lot more time, doesn't really provide significantly higher insights. And then if you have certain compiled binaries, make sure that all those appropriate compiled binaries are included, and you have some time snapshot capability so that you can start these simulations from a certain point and keep running them just for optimization of your time. The third piece that is very important is documentation. This applies to both phasor domain as well as EMT models. And the documentations are very important. You have to be very deliberate with the documentation. Poorly documented model is as good as not having a model at all. So having a reliable or releasable user guide with parameter definitions, allowed ranges, control descriptions, and operating assumptions is very important. It should also include some sort of a model development and validation report that allows the user to kind of look at the model and kind of understand how the model has been used and how it stacks up against actual grid behavior. And if there are some known deviations, they need to know how these or where these deviations show up so that they can factor those in as they do their simulation studies. So moving to the next slide here. Model development is important, but then verification and validation of this model is important as well. There are a few items that need particular attention here. One is model parameter verification. This is an exercise where we ensure that all model parameters, they actually match the facility settings, the facility ratings. They are generally done using OEM data, and it is very important to have documentation to make sure that the parameters that have been provided with a certain model are actually verified. The next phase is model validation, which essentially involves comparing the model responses against the facility response and making sure that the model can actually replicate the facility at hand. That kind of lets us know that the model is good, a good representation of the facility. And if I'm running a study using such a model, then the results are something that we can rely on. The results are something that we can use to identify problems and then later on find mitigating solutions. There are sets of data that need to be collected to make sure that we can go through the model validation exercise. The electrical system data, it includes things like information about cables, voltage regulation in the facility, impedances, transformers, any reactive devices, filters, etc. We need to collect that data. We need to make sure that we have the MVA ratings. We need to make sure that the model represents the rating of the facility, and then the control and protection settings so that we are able to replicate the right-through behavior of the facility. Now, for this validation exercise, there is a need for event and continuous measurements. The event-based measurements are things like DFRs that allow us to record the very fast dynamics, and then once those events are available, we can use that event data to kind of validate the model. If the parameters are not tuned properly, that provides us an opportunity to refine the parameter tuning so that we can replicate the facility response. Continuous measurements are using devices like PMUs. You can also use SCADA, but SCADA has a very slow a very low sampling rate, so they can just be used to understand the very slow changing behaviors of the facility. But things like PMU data, etc., can be used to understand the continuous operating characteristics of the facility, and that can also be used as a data point to sort of validate and refine the parameter tuning of a particular model. So moving to the next slide here. The model quality tests are another key components of the whole modeling exercise. Model quality tests ensure that as a transmission service provider, or as an interconnection authority, or as a transmission planner, if you're being provided a particular model, the model is good enough to be put in your planning studies, to be used for your interconnection studies and such. So there are a set of studies, there are a set of tests that one needs to run to make sure that the model is actually good enough to be put in those or to be used in those simulation studies. There is a flat run stability test. Essentially, the model should be able to initialize and run with no visible jiggles or wobbles in the output of that model. Ensures that the model has been coded properly and there are no numerical issues with the model. There is the voltage and frequency write-through test. Essentially, you want to put voltage dips and frequency deviations at the terminals of this model, and make sure that the model response replicates what the system should be, or what the facility should be doing. Essentially meaning that if the facility is supposed to write through those frequency and voltage disturbances, the model response should sort of replicate that type of behavior. The model should not be tripping off or anything. Then there is the phase angle jump test. Essentially, if you put sudden voltage shifts, it should be, the model should show the ability to remain connected if you have a phase jump tolerance requirement for the particular facility. So you need to make sure that the model can also replicate what the actual facility does. And then there is a control load change test, which allows you to rapidly or slowly change the set points of the P and Q of that particular model. And the model should be able to essentially replicate or follow those commands without getting into any kind of an oscillatory or numerically oscillatory behavior. So again, very important pieces and things that one needs to take care of. So moving to the next slide here, this is probably the last slide. The guidance document also provides recommendations on what we should be doing to make sure that we are able to develop better models. We are able to create models that are useful for transmission planners and planning engineers, as well as interconnecting engineers and all kinds of engineers to run the studies and do their assessments. There are a few recommendations that we have in this particular report. These are the standardized modeling requirements, establishing clear guidelines and minimum data needs for both positive sequence as well as EMT large load models. Generic library model development, especially for positive sequence studies, there is a need to create these generic models so that users can take these models and use it for the studies. Even for large load facility owners, they would have an opportunity to kind of leverage some of these generic models and maybe tune them to replicate the response of the facilities and provide those models. So there is definitely a need for those generic library models. EMT library models, generic models are also useful. They're more educational in terms of their users, but those models can also be used as templates to develop facility-specific models. So definitely have those models are useful as well. Model quality testing and validation guidelines. So we need to implement structured testing, verification, and validation to ensure trustworthy model behavior. This is going to be very important as we step into the interconnection processes and the interconnection studies for these large loads. A lot of these large loads, a lot of these processes will require getting these models from these large load facility owners, but having a proper model validation and verification processes is extremely important to make sure that the models that are being submitted are actually a good representation of the facility that is interconnecting to the system. last but not the least, the modeling exercises cannot be done in silos. This requires industry collaboration and integration. There are modeling experts. Modeling experts can only develop models based on the knowledge that they have, and the knowledge lies with original equipment manufacturers, it lies with facility developers, etc. So there needs to be a lot of coordination between people who are intimately involved in the exercise of modeling with people who have an intimate knowledge of the facilities and the equipment. So again, those collaborations are key for us to have better models as we move along as an industry. So that is the last slide that I have. And with that, I'll pass it back to Alex. And back to you, Alex.
Thank you, Parag. We can just go right over to our next presenter. So go ahead and take the screen. And we'll go right along here.
Okay, thank you, Alex. Good afternoon, everyone, and good morning if you're on the West Coast. I'm excited to talk to you all a little bit today about large load performance requirements, which is certainly an area of interest across the industry. This was an extremely engaging project team. I've listed the contributors here. Similar to what Parag mentioned, we had 4 stream leads. Eric Mayer from ERCOT led establishing what are behaviors, capabilities, and limitations of large loads. Mohammed Shamsuddin then took that and with his team worked with establishing what those performance requirements would try to address. So really power system impacts that performance requirements would be looking to address. Sam Switzer from Meta was our lead for engaging with the load community. I got a lot of great information there. And Taya Mariji from Orsted supported us with doing a review of international standards that exist at the time when we were doing the analysis for large load interconnection requirements. So really thank you to everybody that's on this list. Thanks for your engagement. Thank you for your contributions to the reports. Our project team is actually producing 4 reports, so we're really excited about sharing those with the broader ESIG community in the near term. So jumping into the content, as Alex noted up front, and I'll just touch on this a little bit. These new large loads, they have high proportions of electronics, and they also have new high impact behaviors. These are 2 things we really need to be cognizant of. And certainly there's a high power density as well. Very large facilities, small footprints, fluctuations, ride-through considerations. And so we're at a point here where development is accelerating. And similar to what happened with IBRs, I think establishing requirements for performance is lagging the integration of these facilities. And so that's where a lot of the urgency came about with this task force and putting together these requirements. So jumping ahead, what we're going to talk about today is characterized in these buckets. We do have requirements in the report around reactive power capability and modeling. Parag did a great job touching on modeling already, so we're not going to elaborate on that too much in this webinar. And the reactive power capability piece, we'll let you all read up about it in the reports. Just in the interest of time today, we're going to focus on the topics that are in blue. So jumping ahead to voltage ride-through. This may be some review for some folks, but we want to set the context before talking about the requirements. So VRT is the ability for a facility to remain connected to the power system during and following a disturbance. And I'm making this point specifically because if you talk to the load communities, not from the utility perspective, but from the actual large load developers, to them, voltage ride-through means that their processes continue regardless of the grid's condition. So they're both different perspectives on ride-through. So we want to calibrate to say here that VRT in the context from a grid perspective is the ability for these facilities to remain connected to the power system during and following a disturbance. Inability for ride-through, and we've seen some of these events on the system recently. They can trigger frequency excursions. There's certainly potential for high voltage conditions, thermal overloads, cascading outages, transient instability, voltage collapse. You name it, the size of these facilities, and as they become more prevalent, if they fail to ride through collectively, your post-contingency configurations that you expect are going to be drastically different than what you get. And so it's really important for us to have predictability and stability in our predictive analytics. So moving ahead, today, and again, this may be a review for some folks, the bulk of the IT-related equipment follows right-through characteristics established by the Information Technology Industry Council using what's called the ITIC curve. However, these are focused on serving internal reliability needs of these facilities. They don't actually cover what the grid needs in terms of performance for ride-through overall. So this does not cover the grid's needs, which requires us now to introduce a different set of ride-through characteristics to ensure that the grid is able to behave in a predictable and reliable way following disturbances. And so with that, we're developing dedicated large load VRT curves. So looking ahead, we did a comparison of how different jurisdictions across the world are looking at ride-through. And what we found is each jurisdiction is looking at their own philosophies, protection philosophies, what their clearing times are, what the type of protection, different types of protections that they employ, whether it's power line carrier, whether it includes POTT, DCB schemes, and they established curves that represent what they expect to see on the grid for fault levels, so the voltage for different fault types, as well as the clearing times for those fault types, and they've established curves accordingly. And so, the top curve, if you look at LVRT, there's certainly quite a bit of variability there, and that's reflective of those jurisdictional specific behaviors. On the HVRT as well, different approaches to the same problem, but again, founded in what that utility expects to see in their footprint following a fault. So what they allow, where they allow their continuous range to operate until what the temporary allowances are within the system. So there is that jurisdictional specific flavor to these. So overall, what we've determined is, develop ride-through curves for high and low voltage conditions based on your local, delayed, and remote fault clearing times on any given part of the system. Consider respected contingency events. So three-phase faults, normal clearing time, single line to ground faults, delayed clearing time, for example. We're going to touch on active power recovery in a moment, but consider the timing of active power recovery. Automated post-contingency actions should also be considered if they are leveraged to maintain voltages within acceptable ranges, and also where you're starting from, what your normal voltage operating ranges are. Moving ahead to multi-disturbance ride-through. So multi-disturbance ride-through is something we've come across in discussions with some of the data center and crypto mining facilities, and some of them we've heard the words 3 strikes rule come about. And what that means is after 3 strikes, some of these facilities will disconnect from the power system. And if you think of that in the context of normal power system operations, if you have a common tower contingency at P7 and you have 2 unsuccessful reclosures, 1 for each line, that would be 3 strikes. So for a normal design contingency that is permanent, you could actually have these facilities come off. And so what we're recommending here is to disable this counter-based logic if possible. If not, make sure it's coordinated with what you expect during normal operations, but also what you want to see during more extreme events when you have storms coming through your jurisdiction. We did an industry scan of what this looks like. And so in FinGrid, for example, they require the load facilities to ride through for 10 bolted faults over a 90-second period. Look at Alberta. They expect a minimum ride-through duration of 1 or multiple faults in a 10-second window. So for a 10-second window, if there are a bunch of different faults that are happening, expectation is to ride through. ATC's talked about 3 ride-through events over a period of 10 seconds. So definitely a little bit of diversity there based on each jurisdiction. But the theme of it is, we need to have some allowance for multiple disturbances to happen before these facilities elect to disconnect. Our recommendation is, if possible, disable this capability. As noted before, active power recovery is something we want to dive into a little bit more. And it's actually an enabler for these load facilities to ride through. So those ride-through curves inherently are very challenging for the large load facilities to meet without introducing some level of load management. And what we've been describing here is that APR is kind of a post-fault recovery of the load that's been permitted to reduce during and immediately following a disturbance. So in order to facilitate ride-through, allowing the load to reduce its consumption. If we don't actually permit active power recovery, post-contingency, what you might find is the load may just end up reducing overall. And as we noted earlier, if the load does reduce and doesn't restore to a level that we expect, post-contingency performance of the power system will be different than how we typically model it. And so what we'll find is that there's potential for different types of phenomena that could impact the stability of the system, including frequency, thermal, cascading outages, and so on. And so let's move ahead and see what different jurisdictions have been doing in this regard. So Tenet at a high level mentions that pre-fault active power just must be restored after the fault is cleared. ATC establishes a 3-cycle timeline for when the load must be restored. EnergyNet, after voltages are restored to a certain level, they then expect the load to begin restoring within a certain period of time. Similarly, FinGrid expects that specifically for different types of facilities, different recovery characteristics. If we zoom in on data centers, after the pre-disturbance voltage level reaches 90%, 90% of the pre-disturbance load must be restored to 0.5. Jumping ahead to ERCOT, once the pre-disturbance voltage reaches 90%, their expectation is 90% of the load is restored within 1 second. And similarly for Alberta, they do expect there to be recovery, but it's configurable based on system strength. And we thought that was a really interesting approach. If you throw the load back in really quickly without considering system strength at the time, in particular following a fault, it could actually introduce more problems. And so what we established as a recommendation is that once you reach a threshold for voltage, begin restoring load to a point that it does not result in any further challenges on the system. So for example, if you're in a stronger part of the system, once you reach 90% of the pre-fault load level, restore back to 90% of the load within 1 second. However, if you are in a weaker part of the system, it may be prudent to extend that time period to being over several seconds to make sure the system remains stable as you recover that load. These are really large facilities, so it's really important to ensure that they don't come back in really quickly and further undampen the transient response. Moving ahead to frequency ride-through, which is more of a global impact of the power system. And so we were looking at finding alignment with what is happening on the system today. What are some of the frequency ride-through requirements that we see in the industry? So we looked at different requirements and we saw pretty good alignment between, the North American utilities on what they're typically following today for IBRs, and similarly in Europe, kind of alignment within their different requirements. And so as we looked into this, we noted that it's prudent for us to look into having these large loads meet the requirements specified in NERC PRC 29 for IBRs. And that includes ride-through curves as well as tolerance for rate of change of frequency. So this is a alignment with what we see with other electronic-based facilities. We felt it would also be good to align on those for frequency ride-through. Jumping ahead to phase jumps, very similar to other electronic-based equipment that's on the system. There's an interface between the system and these facilities with the PLL, and it really helps ensure that these facilities are synchronized with the system. And so PLLs are very critical in ensuring the behavior of these facilities remains predictable. And once a PLL fails to actually track the fundamental voltage waveform of the system, your active and reactive power consumption can certainly be altered, which can cause some challenges. And so we looked into this in the international market. And we noted that in Europe, there's a varying degree of tolerances that are noted for phase jumps. 20 degrees in EnergyNet, 30 degrees in Tenet, 30 degrees in Finland. In Canada, AESO has been adopting plus or minus 25 as well. And other than that, we didn't see that many jurisdictions at the time of our survey noting anything for phase jumps. And so what we're proposing here is that align again with what's in PRC 29 for 25 degrees for similar to what is there for IBRs. However, it's important to look at this from a study perspective as well. If there is potential for you to exceed 25 degrees in the part of the system where these facilities are connecting, we believe that that's something that should be covered in the interconnection study and identified as a requirement outside of what is currently prescribed in those standards for IBRs. So generally, the approach is if the phase jump you expect to see for design contingencies and design scenarios is less than 25 degrees, establish the NERC criteria for IBRs. If it's larger, provide a specific criterion in that case. And I know I'm going really quickly, but we certainly have a lot to cover in a short period of time. So jumping ahead to ramp rates, these facilities we expect to exhibit quite a bit of variability. And I want to go back to what ERCOT, saw early on. This is actually in 2024, that they were running out of regulation capability, AGC, during some of the ramp events that they saw. And that was, again, several years back. And as we see further proliferation of these facilities, the expectation is there's going to be some stress on AGC if these behaviors are unmitigated or uncontrolled, or bounds put around them to ensure that there's a balance between the needs of the data centers as well as the ability for balancing authorities to control their area control error. So, generally the way we look at this is changes in active power that are in the second to second or minute to minute range are going to be controlled through some form of automatic generation control. The cumulative impact of those minute to minute changes can be handled at the next dispatch interval, kind of reestablish your automatic generation control capability. But within those intervals, it's certainly going to be handled through your frequency control mechanism. So we looked at different ramp rates that are established on the power system. We've seen some really high ones, 60 megawatts per minute. We've seen 10 megawatts per minute. We've seen 25 megawatts per minute. And others are going to be defined on a case-by-case basis. And so from our perspective, to really ascertain the ability for your system to take on the ramps that these facilities can actually have, it's important to look at what you have today in terms of your philosophy. So if you're today, you're barely controlling ACE with your current frequency regulation regime, and you're going to be adding, several of these facilities, it's important to look at the cumulative impact of those facilities on the potential regulation of your system. In discussions with the large loads or leveraging, what the industry standards today are on what those profiles can look like, superimposing that on what you have today as your actual ACE and seeing what happens. With that, you have a couple of decisions you can make, and I think it's probably going to be a balance. One is to increase the amount of regulation service that you have. The other one is to put restrictions on some of these facilities to ensure that they're not varying too quickly for the system to handle. As we note in the report, I think it's going to be a cross point between the two, where there is some additional regulation that may be required to manage the variability, but also ensuring that these facilities do have the appropriate bounds on their operations to not disturb the system too much. So that's generally how we're looking at approaching this. And there's different ways to look at how to control ACE, depending on the jurisdiction that you're in and the regime that you have. So it's very important to look at it within the specific context that each balancing area has. So moving to another form of variability, we've seen some of the profiles that come with these facilities, and there is a cyclic nature to their consumption. So they can go up and down every few seconds. It could be every 3, 4, 5, 6 seconds. And notably, this coincides with some of the natural oscillatory modes that exist on the Eastern Texas and Western interconnections. So certainly an area for us to really hone in on. And so when we get feedback from these facilities and they provide potential load profiles, or we leverage the ones that are in the industry today, I'm reminded of a small generator, back in 2019. That was oscillating every 4 seconds, but not a huge amount, but that resulted in several hundred megawatts of swings across the Eastern interconnection due to exciting the natural oscillatory mode for the Northeast, Northwest, South frequency mode name. So if you look in the table that we have included here, the third row is the one that was excited in that event, and it caused oscillations starting from the southeast, expanding all the way into northern Manitoba, which is across the entire Eastern Interconnection. So given that, what are some of the utilities around the world doing? So what we found is that there's a little bit of positioning in these requirements, but not necessarily specificity. So FinGrid and Tenet, mentioned that if the load could cause force oscillations, they need to be avoided at those oscillatory modes that are of concern, and potentially installing compensation devices like eStatComs, battery energy storage, to smoothen out their load profiles. Similarly, ATC notes that there needs to be some detailed studies to ensure that they don't actually trigger any of those natural oscillatory modes. And in Canada, AESO stipulated that for large load facilities, they again need to be designed to avoid amplifying or contributing to oscillatory modes of concern in the Western Interconnection. So overall, from a recommendation perspective, I think it's important to start from a low frequency oscillation cycling perspective, that we not encourage or permit the introduction of those types of oscillations onto the system. They can be unpredictable. The system is changing, and those natural oscillatory modes can change as the system changes. So there can be requirements imposed that significantly limit the magnitude and frequency of these potential forced oscillations, so they don't actually trigger any problematic behavior. If there is any residual low frequency cycling behavior that cannot be mitigated, there needs to be detailed analysis to ensure that those considerations are factored in as the approvals are being put in place. So the approach that Europe has taken with asking for a smoother load profile is something that actually some of the load facilities and the technology companies have investigated themselves. And there was a really interesting paper, and it's referenced in the report that we're going to be publishing by OpenAI, NVIDIA, Microsoft, where it talks about different ways to smooth out their load curves. And they talk about a four-pronged approach. One, introducing some level of software mitigation, where they introduce secondary processes to help balance the load profile. Another is introducing GPU limits, so putting floors and ramp restrictions on the GPUs to provide a little bit more of a balanced loading from a hardware perspective. Introducing rack level storage to also help smoothen out the curve, and even facility level storage as well for larger facilities to help balance overall how the facility is behaving. And what they found in that paper is it's quite effective when you combine those different approaches together, and they actually recommended looking at implementing a combination of those to really manage the load profile. So certainly there's a lot of research happening in this space now. I've heard of other approaches, starting to come up as well on managing those kind of larger oscillations. And so we're hopeful that, by continuing to collaborate with some of the technology companies and having good open dialogue with them, that we can arrive at a point where, large oscillatory behavior can certainly be avoided. Jumping ahead to a different type of frequency cycling. So this is a high frequency cycling. And so if you think of in the context of a load profile, the low frequency cycling would be the envelope, and the high frequency cycling would kind of be the chatter that's around the envelope. So we can look at this as like really cyclic inter-second active power variability. And if you think of some of these large loads, we're trying to site them close to generation facilities. And it's something we need to be sensitive about, because if there are mitigated high frequency cycling instances, that can actually trigger subsynchronous torsional interactions with the shafts of those facilities. And so we've included here is just an example showing that for a multi-mass model, we ran some simulations with different frequencies of oscillation and magnitudes of oscillation at a data center near a generator. And what we found is there's certainly potential for torsional interactions. And when you see torsional interactions, you have to establish whether they're harmful. And so manufacturers generally have shaft ascend curves so basically counter shaft torque versus number of cycle curves that depict when you actually are in a range that could be harmful for the turbo generator shafts. So if we look at the curve that we have included here, if you're in the area where this curve tapers off, this is called the continuous region. Any oscillations that are kind of in this magnitude of around 1 per unit could potentially be acceptable. However, if you're in a range where you're introducing a shaft torque of 2 per unit or 3 per unit, you're actually in an area where you can damage the shaft. And it doesn't take that many cycles. So if you think of 10 to the 3, 10 to the 4, and these facilities are oscillating multiple times per second, this can happen relatively quickly. So this is really important to consider when you're siting any of these facilities and allowing the variability to happen near any of the generating stations. And so this is something that we've been looking into quite a bit. So if we move ahead to what different utilities have been doing, Alberta's put in quite restrictive at this point, and I know there's stakeholder engagement and progress on this requirement, so I don't want to comment it as it being set in stone, but relatively restrictive requirements on high frequency oscillations. FriendGrid's done the same thing. They must not cause amplification of any of the oscillations or cause cyclic power fluctuations. It's a firm must not. In the ATC, given the investigation they did on their system, and it's specific to their system, limiting the oscillations over a period of time as well. Since this analysis happened, Southern Company has also released their requirements, and they're looking at about 1 megawatt of variability allowed overall. So our perspective on this, just given the risk to the facilities that are very expensive on the system, is again looking at ways to prevent the introduction of forced oscillations, some of which we talked about just moments ago, that are currently being researched. And if there is a need to introduce those, if there's no way to fully mitigate the high frequency cycling, is to do detailed analyses to ensure there's no risk to generation that's nearby the large load facilities. Jumping into monitoring, and we'll be relatively quick here as I know I'm probably eating into Kyle's time. I think it really is about, the nature of these facilities. It's important for us to get visibility at a high resolution as to what their behaviors are, to really help us have a feedback loop for modeling, diagnose any abnormal behavior, and also ensure that if there are restrictions put in on the facility's behaviors, that we're actually able to do the analysis to ensure that there is compliance with those behaviors, those requirements on those behaviors. I've included several requirements here that have been issued. I think in Europe they have some relatively well-established procedures around this. There's recording requirements. We've now seen in North America that there's now also streaming requirements for active monitoring in operations as well. And so, our perspective is install monitoring devices that can both stream and record high fidelity data, high resolution data, and maintain the recordings for at least 20 days, consistent with PRC 28, and ensure the sample size, the sample rate is reasonable to capture the phenomena that we're looking for. And in this case, we're recommending a minimum sample rate of 100 hertz. So thank you all for your attention. I know we've gone probably a little bit over time. So with that, I'll pass it back to Alex.
Thanks, Ahmed. We'll just jump right into Kyle here. Thank you.
Thanks, Alex. Can you hear me okay?
Yep. Thank you.
And can you see the slides all right?
Yes, I can. Actually, if you could speak up just a tiny bit, might be helpful.
Well, I think I might have to change the mic. Is that Alex any better?
A little better. Yep, that sounds great.
Okay, great. Good afternoon, everyone, and good morning to those on the West Coast. Kyle Thomas here, VP of Engineering Compliance Services with Elevate Energy Consulting, subgroup project team lead of the interconnection process team. So excited to share our team's work on this report we pulled together over the past 12 months or so, and give you an overview of what we've captured. And the report isn't published yet, but it's coming soon in the final stages of editing, so you'll get to see it in the very near future. And there's obviously a lot of touch points with all the work from Parag and Ahmed that they just covered that tie closely with the interconnection process. So we'll talk about that as well. So overall, our objective and scope of this project team, just to kind of recap it, our goal was to take a look at what's been occurring historically with loads and in recent years, large loads in the interconnection process. What lessons can we learn from the overhaul and changes to the generation interconnection process via IBRs that we could learn from? Identify gaps and issues in the industry, the various jurisdictional considerations to look at, and then ultimately develop. The core objective and goal is to develop some recommendations for a sort of baseline, standardized, and improved large load interconnection process for the variety of entities that are involved in this process, of which it certainly has grown and changed in the very recent months and years here. And the goal with the improvements here is, create efficiency, establish firm, commercial readiness and financial requirements to ensure non-speculative projects are the ones moving forward and speculative ones get weeded out. Encourage the data and model sharing or requiring it. Have change management aspects, and I think this last part is really key, is these large loads are developing and changing rapidly, almost day by day right now, it seems. And so how do we account for those unique configurations and the operational characteristics of these now and into the future? So just as the others have done, we had a tremendous amount of support. So thank you to all of our contributors on this throughout the past year. A whole lot of folks were involved in all of our various calls. We had a number of writing volunteers. And then, our work overall was led by our core 5 subgroup leads, Lingyu Jia, Nihal Mahan, Julie Stimman, Hunmir Syed, and Jeff Zhao. Thanks to them for working through the various chapters that they each had responsibility for, and excited to share our work here on each of those topics. So this is a just view of the report. It's titled Interconnection Process for Large Loads, the Current Practices and Recommendations. And so we really wanted to break this down, primarily focused on the transmission connected large load interconnection process, that transmission bulk power system being the biggest, focus right now, especially the size of these facilities. They're all primarily transmission connected. But we wanted to also make sure we look at, how about the ISO RTO, those large load processes inside those markets and also outside? What differences are existing and functioning there? The regulatory side of this large load interconnection process, there's a lot of activity in this space, so we wanted to capture that and also give some historical reference to interconnection processes that have occurred. And we didn't want to not include the distribution world as well. So this is not a core focus, but we do have a chapter that does talk to the distribution connected, for lack of a better term right now, large load interconnection process. So this would be large load type facilities that connect directly to the distribution system. Specifically think of, under 30 megawatts, under 50 megawatts in size. So large load is more of the type there, but there's a lot happening in that space as well. And how do we consider that interconnection process, state regulatory considerations, and adopt what we recommend on the transmission side where applicable and possible. And then we end with overall conclusions and recommendations. So what I'll cover today is kind of a few sets of key topics in each of these main chapters that you will find in the report in the near future. Throughout this project, we took a lens, I think, in that scope document, and we looked at this overall as we wanted to survey what was out there today across the country and globally where possible on large load processes and queues. What are the gaps and issues that everyone's facing, those lessons learned, and then ultimately provide recommendations for that process. What studies should be done during this interconnection process. Importantly, that part is not getting into Parag's and his team's work on the modeling, but rather assuming and recommending that those models be included and required for every large load interconnection process. What then studies should be done every time or screened for under each of these different types of large load processes. And then highlight the integration with the other ESIG large load task force projects. So one of the things here overall that is very clear is these large loads are connecting everywhere. So there are, very quickly when we got into this with our project team, there are a lot of different types of entities that are dealing with this large load problem. Of course, the transmission utilities, of which there's a variety of types, within an ISO RTO market, without an ISO RTO market, transmission only, transmission and distribution only. And so we wanted to factor in how do we think about these recommendations in the context of, a wide variety of entities dealing with this challenge, and everyone having kind of unique aspects. And also, of course, the ISO RTO world is really critical. And historically, there's been little engagement on the large load process or load interconnection process there. But the just sheer nature of the large loads has driven, a huge amount of changes and involvement and close collaboration in those regions under an ISO RTO. So we wanted to highlight that and just really reflect that there's a lot happening all over, and there are unique differences and challenges in each region. So this, overall report and our recommendations should be looked at as like a fundamental baseline set of recommendations for this large interconnection process. What are the core aspects that are necessary in our view? And then, of course, every region, every entity can tweak that and modify it, for their own specific needs. But wanted to set that baseline of what, we think everyone needs fundamentally. So if we take a look at kind of what that core process looks like at the very highest level, that chart on the right is a good overview of that, right? Starting with that kind of pre-application phase. And a lot of these today do occur, we recognize. But what we have found is sometimes some of these steps aren't done, or they're skipped for any sort of reasons. And so ideally what we'd love to see is that these milestones for every large load interconnection project do occur all the way from the pre-application stage to the various study phases, getting into the interconnection agreement, and then getting into construction and commissioning, very key aspect. And then also importantly, once it goes operational, while now technically outside of the interconnection process, that post-interconnection monitoring and compliance to interconnection rules and requirements, like Ahmed's performance and technical requirements for large loads, is really essential. And, in order to do that monitoring and that compliance activity, those rules and requirements must be put in place at the very beginning stage of this whole process. So it is very much a full cycle that has to be considered. And, overall, in our view, this large load interconnection process should have all of these core milestones. And then, as I said previously, every location, region, state, different entities, they either may add additional steps, enhancements to these, various changes for a whole host of reasons. But the core milestones overall should be there. And one fundamental challenge that is just continuing to develop day by day is who is running these large load interconnection processes. In some cases now there actually might be two of them, one at the transmission utility level and one at the ISO RTO level. So there's just a growing complexity given the nature of these facilities among many different entities that has to be closely coordinated, a lot of communication, a lot of information sharing, more so than we've ever done before, probably on the load interconnection side here. We'll talk about more of that here in a second. And again, we don't go into this substantially in our report, but we make reference to the fact that having the modeling and data requirements in place at the beginning stage of the interconnection process, and those interconnection performance requirements at the very beginning, prior to even starting a large load interconnection, getting those requirements written down, in place, published, and a part of the process are essential steps. Everything you just heard from Parag and Ahmed, the interconnection process is made better by those requirements getting set in stone, and takes a lot of unknown and reliability risk and modeling risk out of the equation. So we highlight that in the paper and recommend closely that, adopting modeling and data requirements and interconnection performance requirements as part of your large load interconnection process. One of the things Parag talked to a good bit, and so did Ahmed, and we touch on in ours, is once those models and the data is available and those performance requirements, throughout that interconnection process, there are a variety of studies that likely will need to be occurred. Some should occur every time, and then some might need to get screened. So we provided this kind of set of the overall reliability studies for large load interconnections that can be done, and then kind of highlight the fundamental, kind of called tier one, the RMS studies and screening analysis, right? So that's your power flow studies, your short circuit analysis, dynamic stability studies, and doing that kind of risk-based EMT screening. So looking for interconnections where, for a whole host of different criteria, such as the size of the large load facility, the system strength in that region, and its proximity to sensitive, complex equipment like fax devices, HVAC systems, maybe even other critical customers or critical pockets of large load facilities or IBRs. Or facilities that have a highly cyclic load pattern that Ahmed mentioned, that AI training world. If you go through those screening criteria and apply them for a project by project basis, you'll find, which of these types of projects, are, essential to perform EMT studies. And once you get into that space, there's a whole set that Ahmed just kind of captured a lot of, but the detailed EMT-based subsynchronous oscillation study, the damping and control stability type of studies, and then the power quality studies looking at your harmonics, your voltage flicker, and others in that kind of local region. This is not a comprehensive list at all, but this is the type of detailed EMT studies that will need to be looked at, under that screening criteria that we highlighted in the paper. You're also looking for other types of power electronic interactions that could occur, controller interactions, as well in that region where you might have sensitive and large other complex equipment. So I mentioned before that one of the aspects of this project that very quickly we got into a lot of discussions about was the various different types of transmission entities and how there are some specific nuances and differences that ultimately change in some aspect the process elements, the timing, the interface, and the coordination during this large load interconnection process. So we've got a few terms here that we highlight in the report. So first is TDU, that's just the transmission and distribution only companies, so those that don't own generation. We've got vertically integrated utilities, that's VI, and those that are within an ISO RTO market, and then those that are outside. And so there are just unique differences that we highlight throughout the report. You can see this table that gives an example of some of that criteria. And then, of course, your distribution entities and cooperatives and how they are handling these large load interconnections as well. The study timelines vary. The interface with the customer varies. So you might have multiple parties involved, such as in an ISO RTO, you've got the transmission entity in the ISO RTO. So where that customer interface lies, how is that then coordinated and shared among the different transmission entities is essential. Where do the technical standards lie? Who is applying technical standards and requirements? Do the large load interconnections have to apply to all of them? Is it a shared hybrid set of requirements? All really key things that we highlight and talk about where close coordination between multiple entities in some places is absolutely required to make sure there's a consistent, standardized set of standards and requirements. Whereas in other regions, it's just one entity. In the non-ISO vertically integrated case, it's essentially just one entity for the most part that coordinates a lot of activity. And so there's some flexibility there, but then there's more impetus on that company to define all these set of requirements and policies in place holistically across the board here. We also highlight, resource availability, and this is tools and staffing overall under this massive influx of interconnection projects, just like we faced with the generation interconnection queues. That varies across these organizations is another challenge overall. And if we can make standardized, kind of uniform interconnection processes for these large loads, that will certainly help all aspects to be as efficient as we can, and what limited resources we have with competing priorities, be able to be as efficient as possible with these large load interconnections overall. So on the ISO RTO side, there are so many activities going on in this space that we highlight. each of the kind of different regions and some of the latest developments. And to be honest, at the time of us writing and doing this, there's stuff that is happening today, for example, where we probably don't have the latest and greatest. So we might have to look at reviewing that and trying to keeping that up over future iterations potentially. But what we wanted to just highlight here is that historically before this influx of large load interconnections, the the responsibility for these load interconnections was historically always been these transmission utilities for the most part. And the ISO RTO is responsible for that generation interconnection and transmission planning activities. But with the large load influx, their enormous size, their rapid growth, and critically important that their new types of configurations where they are co-locating with new or existing generation, that's forcing that closer coordination between the transmission entities and the ISO RTOs, more data and information sharing so better forecasting can happen. But it's also starting to blur the lines between, okay, well, this is a large load interconnection, but now we're also adding generation, or we're impacting the transmission planning substantially enough that the ISO RTO needs to be involved as part of their key roles to support the generation, interconnection and resourcing and the transmission planning aspect. So you're seeing a rapidly evolving space on these large loads at the ISO RTO level, with new policies being made, new structures being made to account for these types of facilities and their kind of ever-changing arrangement with and without generation, and also even with and without firm transmission service versus flexible transmission service, or interruptible, if you will. So that flexibility term starts to introduce a whole lot of questions. And so this is a rapidly evolving space. We've got some highlights here in each of the regions and a couple of examples here I'll just briefly mention. So critically important, that this world in the ISO RTO large load interconnection process will kind of probably continue to evolve rapidly to meet the demand of these facilities in that ever-changing world of co-location, and how do we actually bring and develop generation along with these large loads, either kind of bring your own generation concepts or other aspects. So we overall highlight that however these policies develop and adjust over time, the core set of baseline recommendations that we give in the paper should still apply kind of across the board. That uniform set of steps and milestones and transparency and information sharing, regardless of how these things evolve, those aspects should be maintained to help make efficient, fast processes to interconnect these large load facilities to the best extent we can, while not jeopardizing bulk power system reliability overall. So of course, two of the most major, I'd say, that we highlighted here, SPP's high impact large load policy, and their the HIL policy, and then the HILGA, the high impact large load generation assessment processes. They were actually approved by FERC in January, and starts to define, from the SPP system, the definition for large loads, the thresholds, the requirements, and the studies that perform within, often very, very quick timeframes for those high impact large loads. And importantly, also, when you think about the supporting generation that either gets added with the large loads or in the future with those large loads, that's that HILGA process. And there's different new types of arrangements and considerations here, whether that generation is at the same point of interconnection with a large load. This has been kind of various places have been coined, energy parks or whole little microsystems, if you will, although now we're probably at the macro level, just the size and scale of these. There's also the concept of that local area where you have nearby generation, 1 or 2 buses away, that are directly in support of that large load facility. And so these types of processes, are going to start to get implemented and start to change that landscape there in SPP. And then in the PJM world, FERC actually gave, 4 new types of arrangements with large loads, very similar to the concepts of the generation plus the large load, very, very close. And they had given orders for PJM to account for these types of options in the, co-located generation and large load world. So, this is front of meter network integration, transmission service, new firm contract demand for transmission service, the flexible arrangements, if you will, that non-firm contract demand, and then this new interim network integration transmission service. So We'll see how those continue to get evolved and updated and processed, and just further makes the complex arrangement of these facilities, accommodated by our different regions across the country here. So what we wanted to overall highlight is on the regulatory aspects here. So there's a lot that we can learn from and a lot that other regions around the world have already taken steps for that we can use as examples of what we can do here. And we want to take a step back to look at the generation interconnection world. That chart on the right really just kind of shows that there's a tremendous amount of similarities between the generation interconnection process and the large load. Everything we've just lived and gone through over the past 15 years with the generation interconnection overhaul, we're in many ways reliving that again in the large load. Obviously with some unique and massive scale differences, but the fundamentals are still very much there. There's that need for queue management processes, interconnection requirements, modeling requirements, commercial readiness, minimizing speculative projects, and standardized milestones and study processes throughout that process. That world of that generation interconnection literally addressed those via FERC orders, back from the original one of Order 2003 all the way to the most recent Order 2023. Through that, we got standardized large generation interconnection agreements, large generation interconnection procedures. And if you look back at those, we just wanted to highlight the goals there are fundamentally very similar to what we're looking for today. Expedited generation interconnections, transparent, non-discriminatory market entry rules, preserving system reliability, and ensuring rates remain just and reasonable. So those fundamental goals there align with, I think, what we're all trying to get after for these large loads at the same standpoint. So we will see what comes out of this, but of course, one of the largest things from last year was the DOE letter and the FERC ANOPR on large load interconnections with the 14 principles. And if you look at those and read through those, there are some many similar frameworks and goals for large load interconnections that are laid out in the kind of FERC order 2003 to 2023 on the generation side. So, there's some things we can learn and maybe adopt from the LGI, LGIP process for large loads potentially. And if we look at across the pond, if you will, the EU, they have their demand connection code, the DCC, and they established that initially in 2016. And it set mandatory technical rules for large load interconnections. Now, some of that is very much technical requirements and modeling requirements. A lot similar work from what Parag and Ahmed and their teams just did. But it does actually also talk about process steps that should be uniform across the board. The data and model sharing, cost allocation, material modifications, what happens under operational arrangements or emergencies, if I need to reduce load or if I have more demand or backup generation, all those types of information sharing and understanding how these facilities work in that interconnection process are laid out here in that DCC code. And so overall, this is just to highlight the past work in the regulatory space that has existed on the generation space and what's kind of currently out there in the large load. And I think that, fortunately, we have a lot of regulatory policies already available and in place that we can take our lessons learned and adopt for large load interconnections very quickly. And, there's a tremendous amount going on in this space already this year. And so I think we'll see a lot more coming out of this year, especially from the ANOPR and other policies and all the NERC activities that are coming on this large load space. So more to come on that, but just wanted to highlight all the great work and past work that we can reference here on this regulatory space. And then kind of my last chapter overall is on the distribution large load interconnection process. So we, again, wanted to highlight the world of the distribution large load interconnections overall. And one of the first questions is, well, what is a distribution large load? And so we created a set of the table there of just kind of the common types of large loads. Now, again, that's just kind of aligning to the new term and the new name. The scale of the size obviously is in the distribution world. So, say 1 to 30 megawatts, maybe 50 megawatts at absolute maximum. But the facilities are often very similar, especially the small enterprise data centers or the large ones. And then a classic set of facilities that we've had of large loads for many, many times, many decades, excuse me. And we've been working to interconnect them for many decades in handling their reliability impacts. One of the key examples being arc furnaces. There's a lot of similarities we can think about of how we've handled arc furnaces on the system to what we're trying to work on now with large loads. And these same challenges that we just highlighted with the transmission world exist absolutely the same in the distribution, albeit it's kind of an even smaller set of resources and help to address that. The distribution world, it's usually typically entirely state level, driven regulations and policies, and also utility level rules and processes on these interconnections. So we wanted to highlight that and just really highlight that the distribution process can be supported by adopting many of the same baseline standard steps that we've defined in this report. Can help make the distribution interconnections be more efficient and supported more, and also highlight that as the distribution system continues to interconnect these and especially more complex facilities, if you're doing the new data centers at the distribution level, that probably also warrants closer discussions and information and data sharing with transmission utilities and ISO RTOs than we maybe had to do in the past. And in some ways, it's kind of similar to what we're in real time right now going through with the distributed energy resources and that close coordination of the DER and distribution systems, and how do transmission utilities model those, study those, and understand their operational impacts on the system. And I think the last slide here, I'll leave this up and happy to answer any questions. What we took all of that work overall and wanted to leave the report with kind of one key figure overall, and this is a early draft that is in the report now, but that we're going to work on making kind of more polished and pops a little bit more. But we took all of our recommendations for this baseline process and we built this kind of fundamental core ideal interconnection process for large loads with our key recommendations of all the details that go into this process that should be considered along the way there. So that readiness phase one, this is that viability filter and making sure that the information is provided at the very beginning with that application submittals, data packages, checking financial and site control, and moving on to from there. If you pass all those checks, you get into the study phases where you're now doing the technical studies, all the studies that we just mentioned, the power flow, short circuit, dynamic studies, and screening for EMT, and then running EMT where applicable, creating that kind of final study set of reports and findings. And importantly, if there's the ISO RTO involved in this stage, those two, between the transmission entity and the ISO, are key factors in this study phase to make sure those studies are aligned between both sides and coordinated. And you don't move forward until all those studies at both sides are fully executed and understood. And then you get into the commercial commitment of understanding, okay, we've done the studies, what network upgrades, interconnection costs exist, finalize all those, and the timeline for how long, depending on the type of service being sought out. You get into that final step and you get into the interconnection agreement and you move into the commissioning and operations. And so throughout that whole aspect, those key recommendations at the bottom are some of the key items that we've highlighted that need to get addressed throughout each of these steps. Things like the material modification rules, the withdrawal penalties and exit penalties at various stages, the application package, the modeling requirements, the technical performance requirements, the dedicated milestones, and then of course the close coordination and arrangements with the ISO RTOs from the transmission planning impacts and the generation resource impacts as well. So with that, I will leave it there and happy to answer any questions, and I can certainly pass it back to Alex for a roundtable for the whole group here.
Thanks, Kyle. Just on time here. So what we'll do now is we'll have our questions and answers. Parag had to leave us, so we'll do just myself and Kyle and Ahmed here. There are a lot of modeling specific questions on the Slido, so we'll take some of them that we all can answer, and then kind of the more specific, detailed modeling questions we'll handle as Parag will write those answers out. We'll provide them with the recording and the slides at a later time. So we'll answer the questions you can answer today, and then we'll have that wrap us up till the end of the meeting. So Kyle and Ahmed, we'll just get started with questions here. So the first question is, can folks still contribute to these reports I think the answer for that at this point is that these reports are in their kind of final review before publication. So at this point, kind of the big contribution and drafting efforts are over, or we're editing those. But there will be more work, both large loads and other kind of reliability and other ESIG topics. So for those of you who saw the reports or see these reports and think that they would be, or the ESIG materials and task forces, workshops, that kind of stuff, are interested to participate in, that just recommend joining those activities and working through future work items. So if you missed the opportunity on these reports, there will be more efforts coming on this and other topics. So please, if you're a member, join the working groups. If you're not a member, please become a member and join the working groups and task forces, and you can contribute to those future work items. So the next question, and I'm just going to go generally down the list of upvotes or thumbs ups here. This is a modeling question, and maybe you all can add some to it, and I'll add a little bit to it. But the question is, what are the best practices currently for modeling AI data center loads in power system and planning resource adequacy studies? So that's given their unique characteristics, and what are the best practices, and how are they different from modeling other resources? So I'll leave it for Kyle and Ahmed if you want to give an answer to that. If not, I can opine a little bit as well.
Hey, Alex. I can maybe approach it from one of the angles we've been looking at is, in the RMS timeframe, looking at, variable amounts of electronic composition. So if they have 70% electronic composition, and you want to get a better feel of, if that's stretched a little bit, changing the model accordingly. In the EMT timeframe, when we're looking at torsional interactions, if we don't have certainty on the profile, what we've been doing is doing a sweep of different frequencies. And so what that means is we're looking at different envelopes for the kind of lower frequency oscillation, as well as different frequencies for the chatter on that envelope. So we can look at a whole, bunch of different scenarios and ascertain from those scenarios if there is risk with different load profiles. So, in absence of actual specificity, doing a bunch of sensitivity studies in lieu is a really good way of, covering your bases at the time of the interconnection analyses.
Thanks, Ahmed. Kyle, anything to add to Ahmed's answer on AI modeling, or sorry, large load modeling?
He covered it well.
Great. Yeah. The only additional thing I would add is, well, Ahmed just answered is kind of in specific relation to some of the more unique characteristics of the large loads. But that's not to say that we really, not to say that those are the only considerations for modeling the large loads. A lot of the same considerations and best practices that we are presenting here at ESIG, and like in the NERC dynamic modeling recommendations and those types of guidance, all of that will still apply to these large loads. And things like those types of things that I'm referencing are kind of technology specific, vendor specific models with site specific parameters as much as you can. Ahmed kind of pointed at some challenges for that, and verifying parameters and settings. So those things are kind of ubiquitous amongst all modeling. They hold true for large loads, but we also have those additional unique characteristics that are additional challenges on top of those that we see for modeling of IBR. So that's kind of like the square and the rectangle, right? The best practices for IBRs are they also apply to large loads, and then plus some extra for large loads specific and unique characteristics. So the next question, so there's a lot of uncertainty for AI load profiles, and these are the uncertainties kind of are driven by variations in AI training processes. So when we try to figure out what load profiles will look like, what assumptions are, should be considered, so we're able to actually reasonably represent those uncertain load profiles in the model space. I guess either one of you could take it. If not, I can try.
So, sorry, Alex, I think, similar to what we noted in the answer to the previous question, I think that specificity that we're looking for early on in the process, in particular because some of these large load connections are being pushed forth through development arms, real estate agencies that don't necessarily have solid information. And so with that, we've been working with those applicants, with our utility partners to establish kind of reasonable worst case assumptions to look into at the time of interconnection. So in terms of a rock solid answer, I don't think there is one. I think it really comes down to addressing the uncertainty again with numerous sensitivities to cover as many bases as we can without the fulsome information we're looking for.
Thanks, Ahmed. Kyle, go ahead.
Oh, yeah, looking at time. Yeah, totally agree. I think there is a side of, in lieu of not having detailed information of the facilities, can warrant doing, tremendous studies on your system to understand where those risks are. What are the frequencies and the ramping concerns that your system, you can do a wide range of that scan and find out where those problems may lie. And at least now you can say, you cannot operate in these bands, right? You cannot operate at these magnitudes. So at least you're getting now specifics to say you cannot do this. Doesn't mean all the others are fine. Certainly that's not the counter argument there, but it's to say these are definitely no-goes. And if there are others, we need to share that. We need to study it and understand. But these are absolute, like you hit these frequencies and these scales are ramping, then you cannot proceed further. You have to fix those and address them before you move forward. So that's a way to maybe take out some uncertainty by knowing your system really well and finding out where those limits exist. In lieu of not having any other information, you could explore it that way as well. We've seen some folks that have some of the best requirements that Ahmed mentioned that are out there now. They have gone through a 2-year long study set on their system to understand where those risks lie, and that's a key starting point for a lot of folks.
Thank you both. One more quick modeling question before we get off of modeling questions, and we'll answer maybe one other one. There's a question about, because some of the large loads are hundreds of GPUs, and whether aggregation or disaggregation is preferred, or what processes and consideration should be made for that. I'll answer first, and y'all maybe can correct me. But when we talk about aggregation, usually in these reliability settings, we're talking about aggregation of like a dispersed inverter-based resource plant, right? So you're aggregating the collector system to cover voltage drops among collector systems and other considerations with kind of long cables and things like that. For these data centers, since they're so geographically concentrated, they're in a building, the benefits of aggregation are mostly just computation for running those simulations, right? I don't know if there's much benefit for aggregating or disaggregating, or much difference between the actual collector system of this large load. So I guess the answer there is that the important thing is to just model what the load performance should be or would be, and then aggregating and disaggregating is probably up to your own assessment for how much work it may take and what you're trying to study, and if those two things result in the need for doing a disaggregate large load model. So I guess shortly on that last piece, Kyle or Ahmed, any additional clarity or color for that, for aggregation of the large load model?
None from me. Thanks, Alex.
None here.
So
Well
we'll have time for one non-model question, which is, I'm surprised at all the modeling questions. Usually people aren't super interested in modeling. Where was it? Okay, so this would be maybe a short one too, since we're running out of time here. So for entities like ERCOT and SPP, who have already established ride-through requirements for these large loads, have y'all seen any indication from manufacturers of large load equipment or developers of large load sites on whether or not those requirements are possible to be met? And if not, what kind of discussions have y'all seen regarding ride-through and capability?
Yeah, I can comment on that at a high level. I think the large load community is actively involved in all the stakeholder engagements around these requirements. And I think the active power reduction that we talked about in the presentation that I gave, affords them that ability to reduce their power consumption during periods of challenge to facilitate riding through. So I think there's different ways to approach tackling it. I think the large load community has been really forthcoming and wanting to be good citizens of the grid. And so they're looking for ways to actively, ensure that they can provide the expected performance. And, active power reductions during faults is one mechanism. It can also support with local voltage control as well on site. So there are different mechanisms that have been articulated, and it's really about now establishing, best practices.
Thank you. Kyle, any last thoughts before we're out of time here?
All good here, Alex. Thanks.
Great. Thank you both. We're out of time, just on time here. We didn't get to all of the questions. So like I mentioned before, answers to those questions will get posted with the slides and the recording of this. So we're out of time. We'll have to wrap it up. So thank you both, Kyle and Ahmed, and Parag, who, if you listen to this recording, you can get your thanks, but thank you for you all three for coming presenting today. Mentioned it just previously and again earlier. Once the video file is uploaded and posted, we'll send out an email and let you all know that it's up there and posted and available, as well as the slides and the answers to these questions. That'll come from the general kind of ESIG information mailing list, kind of dispersed like you're used to seeing. We appreciate everyone's engagement, including the speakers. We look forward to seeing everyone here soon at more webinars that we hold here at ESIG. We also hope to see you at our spring tactical workshop in Tucson, Arizona, and that's the week of March 15th. This year. That's back at the Lowe's Ventana Canyon Resort by popular demand from ESIG stakeholders. So we'll look forward to seeing you all there. Further information on all the webinars and meetings, you can find that at esig.energy, our website. That's under the events page. There's also a lot of that information in our newsletters and informational emails, and everyone here is invited to attend all of those activities as well. So wrapping up here, last but not least, before we sign off, Kyle, Parag, Ahmed, thank you again. Thank you very much. This is very timely work, very important work. Look forward to seeing you all in the future, and just thanks from me personally for leading these project teams through creation of this kind of massive amount of content that will be released and published shortly. So with that, thank you, everybody. Thanks for coming. We'll see you all at the next one. Bye.
Thanks, Alex.